Welcome back to the calculus of explanations. How do we find the shortest path between 2 points? How do we know when a beam will bend and when it will break? How does nature know how to form the surfaces of minimal energy, or the shapes that will experience the least resistance? How should a boat heading change in order to reach a point on the other side of a river, given a particular flow profile? What strategies can we use to control a rocket's thrust against gravity and air resistance to reach the maximum height and slip the surly bonds of Earth and touch the face of God? Okay, that's a bit dramatic, but still, all those questions and more will be answered in this video series on the calculus of variations. As you might have guessed, this is the field of maths on which the channel name is actually based, so you can tell that I probably have a higher than average level of interest in this topic, and I'm really excited to bring it to you. I was really grateful to see such a positive reaction to my first video series on circle inversion on this channel, and I am really excited about this series. I hope that it'll be quite interesting and have quite a few videos in it. So let's dive in. Consider the famous brachistochrone problem of a bead sliding down a wire under gravity. Which shaped wire has the shortest transit time? See if you can guess from the options given here which will be the shortest. From these four options, clearly orange has the shortest transit time. How do we know which shape has the lowest transit time overall? For this, we need the calculus of variations. To explain what the calculus of variations is, I think it's first useful to look at an ordinary calculus problem, specifically an optimization problem. Let's look at this classic problem where we try to minimize the surface area of a cylinder for a given volume V. Note that for very large radii, as well as very small radii, the surface area should be very large. Hence there should be some point in the middle that has the smallest surface area. Use the volume formula to rearrange the area formula as a function of a single variable, the radius r. Differentiate, set it to 0, and solve for the radius of the smallest surface area can. A really important point I want you to note is that if we change the radius just a little bit away from this optimal point, then the area shouldn't change very much. This is a key insight that we're going to use later on when we talk about the calculus of variations. What's the shortest path between 2 points in the plane? Hopefully you set a straight line. But can you prove it? This problem may seem trivial, but of course it isn't always. We have to show that the straight line is the function with the shortest distance between these 2 points. But how do we do that when there are an infinite number of functions to choose from? To make it a little bit easier, we're going to make some common sense assumptions. For example, this curve isn't a function at all because it doesn't pass the vertical line test. And in fact, we know this can't be the shortest path because it doubles back on itself, going back towards the origin. We could perform a type of surgery on this curve like this, which would always lead to this shorter path. Similarly, loops are not allowed because we could perform this sort of surgery, leading to a shorter path. In the same way, if there are corners in the curve, we know we can always create a shorter curve by cutting across that corner. This should give you an intuition as to why the straight line truly is the shortest path. Alright, let's talk strategy. To find the shortest path, we first need a method of determining the length of a path. For a very small section of the path, we can use Pythagoras' theorem to tell us the length of that segment, and then integrate that along the length of the curve. What we end up with is an expression for the length of any curve that is given by the function y of x. Here we can see 4 different curves between the 2 points. The functional for the arc length is here, and the values that we get for the lengths of the different curves are as follows. You'll notice that this expression involving an integral and the derivative of y with respect to x is a little bit different from the functions that you're probably used to in ordinary calculus. In fact, because they take functions as an input, these are known as functionals. Let's look at the difference between functions and functionals. A function takes a number as an input and outputs a number. A functional takes a function as an input and outputs a number. Our goal is to find the function that minimizes this arc length functional. We're going to do this using something called a variational. The strategy is to imagine that we've already found the minimizing curve, here a straight line, and then to add a small variation to that curve, which we're going to call eta. Notice also how our new curve depends on the parameter epsilon, which you can just think of as a small number for now. Eta is a small variation to the original curve, which vanishes at the endpoints so that y epsilon has the same endpoints as the original curve. Remember how I said this would be important? At the stationary point, or the minimum, as we move slightly away in either direction, the surface area doesn't change very much. It's the same here. If we add just a small variation to this curve, the length of the curve shouldn't change very much. This is really the key insight. The derivative of this functional, evaluated at epsilon equals 0, should be 0. If we perform this operation, taking that derivative inside the integral sign and using the chain rule, we then get something like this. Evaluating this at epsilon equals 0 and setting that expression equal to 0 should give us the stationary path. Since the function eta was arbitrary, we have, for all admissible eta, this equation here. This still looks pretty complicated, but there is a trick we can use. If we perform this substitution here, then we can use everyone's favorite integration technique, integration by parts, in order to make things a little more clear. Since the function eta is 0 at the endpoints, we get some simplification, and we end up with this equation here. Notice that the integrand now contains the function eta. Let's look at one interval from c to d on the curve. Let's imagine on this interval that u' and eta have different signs. In that case, the integrand would be negative, and the contribution from the integral on this interval would be negative. But that would mean that we're decreasing the value of the overall integral. In other words, by perturbing the curve slightly in this interval, we can create a curve with a shorter overall length. This is a contradiction because we started with a curve that we assumed was the minimum length. This is the key part of the proof. Since we can always perform this trick, choosing eta to be the opposite sign of u' in order to decrease the overall length of the curve, in order to not contradict our original assumption that this was indeed the minimal length curve, it means that u' has to be 0 everywhere. This is excellent because it means that we've now reduced the problem to an ordinary differential equation. If we integrate both sides of this equation, we get that the right-hand side is a constant. Doing a little bit more rearranging, we can try to solve for y'. In this line, you can see that the right-hand side is a constant, so the left-hand side has to be a constant as well. The only way that can be true is if y' is a constant, let's call it m, and then y of x is mx plus c. This, of course, is the equation for a straight line, and if we plug in the two endpoints 0, 0 and 1, 1, then we get that c is 0 and m is 1 for a final solution of y equals x. And so, of course, the shortest path between these 2 points is a straight line. In the next video in the series, we'll look at the brachistochrone problem, the problem that really started the calculus of variations as a field. We'll derive the functional for the transit time and use this as motivation to derive the Euler-Lagrange equation, the most important equation in the calculus of variations. Throughout this series, we'll look at a lot of different interesting problems with solutions that come from the titans of the field like Euler, Bernoulli, Lagrange, and Newton. These problems will range over a wide array of physical phenomena and mathematical techniques. Some of those techniques we've already discussed in this video, like variationals, functionals. Soon we'll look at the Euler-Lagrange equations and different variants of it, and we'll hopefully cover conservation laws and optimization with constraints. If that sounds good to you, I hope to see you in the next video. Until next time, stay curious.